Okay, in today's lab, we want to implement a neural network for classifying movie reviews. Uh, we are going to implement three models for classification. Uh, these models will take textual reviews and then classify these reviews into two main classes, positive or negative. The data set we will work with in this lab is the IMDb dataset. This dataset includes 50,000 reviews from the Internet Movie dataset. The dataset has been split into 25,000 reviews for training, and the rest will be used for testing the network. It should be noted that each set consists of 50% negative and 50% positive reviews. As I mentioned earlier, we will develop three models to analyze reviews in this data set and classify those data sets into two categories, positive or negative. The first model we are going to develop uses a dense artificial neural network for analyzing and processing the data set. As you can see here, we first load IMDb dataset. Here we have option num words. And as you can see here, we set num words to 10,000. It means that we only want to keep the top 10,000 most frequently occurring words in the dataset. So if here you set the number of words to 5,000, it means that you are interested in to keep the most 5,000 most frequently occurring words. After loading data, if you look at the, for instance here, training data, you can see a set of numbers. In fact, you know, each record is a list of numbers. You might ask how a textual content has been decoded using a set of integer numbers. I want to explain this by example. Here we have a table. In this table, as you can see, each word is given a code. So it's like a dictionary. You can consider this table as a dictionary. And in this dictionary, we have given any word an integer number. For instance, the code for a word good is 295. Now we want to decode comment comment this is a good movie. We want to convert this textual content to a list of integer values. To do that, we have a look at this table and find the word, each word in this table, and put its integer equivalent here. For instance, here, word this, okay, here, this has code 103. Then word is, its code is 80. The next word is good. Its code is 295. And finally, we have word movie. And if we look for word movie in this table, we can see its code is 4. So as you can see, I used this dictionary table to convert text reviews to integer values, to a series of integer values. So in IMDb, all the textual reviews have converted to a set of to several sets of integer series, as you can see here. So if you have a look at trained data and test data from this data set, you can see a data set of integer values. I have explained how we can how this conversion has been done. Anyway, after loading data, we need to create tensors. You know that the data first is loaded into Python data structure or Python arrays. But cross library is able to work with tensors. To create tensors, we should store Python arrays in NumPy arrays. So as a pre-processing task, we should call this function, function as defined here, to convert Python arrays into NumPy arrays. As you can see here, the dimension or size of each tensor doesn't exceed 10,000. Why? Because here we ask the load command to keep only the top 10,000 most frequently word. It means that in any record, we have only up to 10,000 words, not more. That's why the size of each tensor doesn't exceed 10,000. So here we can see the dimension or the size of each tensor is 10,000 elements. So this function stores these Python arrays into NumPy tensors. So we call these functions for training data and test data to convert Python arrays to NumPy tensors, and now we are ready to develop our model. As I mentioned earlier, for the first attempt, we want to use dense neural networks. So here we generate a model, a sequential model. Then we add 3 layers. The first 2 layers consist of 16 neurons, and the activation function for these 2 layers is ReLU. As you can see here, the input shape is equal to 10,000 because you know the size of input tensors is equal to 10,000. In the last layer, we have just 1 neuron because you know it's a binary classification. For binary classification, we have only you know only single probability distribution of reviews. So the network returns a floating point value ranging between 0 to 1. The 0 value means that the review is negative, and the 1 value represents positive reviews. So as you can see here, the output of this model is either something between 0 and 1. The values closer to 0 means negative reviews, and the values closer to 1 represent positive reviews. So after compiling the model, we train it, and here using this command, we can evaluate the model to obtain its accuracy, and to evaluate how our model works well. Then, if you run this script, you can create a table. This table consists of two columns. The first column shows the real review. So either it is positive or negative. And in the second column, you can find the predicted review for the reviews. Okay, as I promised earlier, in the next part of this lab, we are going to implement this review uh, prediction model using a simple recurrent neural network. Again, we are going to use IMDb dataset. So we first upload this dataset. And as you can see here, again, we set the num words option to 10,000. Here, we perform some padding stuff on data. If you remember, I mentioned that the size of or the number of layers in convolutional neural network in RNNs is equal to the number of elements we have in the input data. Here I explained that, for instance, if we have a record or a sentence including 10 words, we should have 10 layers in the network. And I mentioned that in real implementation, we make all records having the same size. Here, using this padding method, we make all, we create reviews, textual reviews with the same size. As you can see here, we have the option max length. This max length here is equal to 500. It means that we are going to, create an input data set whose record have the same size, 500. Here I have uploaded a data set, and the size of each record is different. We have some short reviews and we have some long reviews. Short reviews consist of few words. Long reviews consist of, I don't know, thousands of words. But here we want to, turn this input data set into a new data set that all records in this data set have the same size. Now I want to explain how this path sequences method works. Suppose this is anyway, an input record with size of, I don't know, for instance, 10. So it means that we have only 10 words in this record. If we give this record to path sequences with max length value of 500, the output of this method will be a new tensor including 500 elements. The first 10 elements will be the words we have here. So here we have 10 words, for instance, and these 10 words are copied into the new tensor. The rest of elements, I mean the 590 remaining elements become zero. So all of the remaining unused elements become zero. So in the end, we will have a tensor including 500 elements. So as you can see, if we have a record smaller than 500 word, this padding command add more zeros to the tensor until the size of this record become 500. But if we have a very long record, including, I don't know, for instance, 5,000 words, the path sequence function truncate, the words which to make the size of new tensor 5,000. So if we have here a tensor including 5,000 words, the path sequences method keep the first 500 words, and the rest of them will be truncated. So as it is mentioned here, this method paths sequences that are shorter than 500 with zero until they are 500 long. Sequences longer than 500 are also truncated. So if we give, input data with an input test data with different sizes, after calling these two functions, we will have text input train and input test data set with records all with the same size 500. After pre-processing data and after making tensors with the same size of 500, now we want to develop our model. The model we are going to develop consists of 3 layers. The first layer is an embedding layer. I will explain why we use this embedding layer. Then we have a simple RNN layer. And finally, we add a dense layer. As you can see, like previous implementation, here we have just a single neuron in the last layer. Now I want to further detail, give you further detail about this embedding layer. If you look at input train and input test data set after padding, you can see, all tensors consist of 500 elements, and the majority of these elements are empty. In fact, input train and input test are both sparse data sets. As I mentioned earlier, the size of or the number of layers in RNN should be as the same as the size of input data set. Because here we have exactly 500 elements in each tensor. It means that we should develop an RNN layer consisting of 500 layers. But the majority of these 500 elements in the input data is zero. So instead of using long tensors, we can somehow compress these sparse tensors and create dense input tensors. To this end, we use this embedding layer. In fact, this embedding layer takes tensors with the size 500 and compress this tensor, this sparse tensor, and return a compressed tensor including 32 elements. So this embedding layer is responsible to compress sparse tensors into dense tensors. And then the output of this layer consists of 32 elements. So here we have input train consisting of 500 elements in each tensor. If we give each record in this data set to an embedding layer, we will have a compressed and dense tensor consisting of 32 elements. Okay, now we don't need to here create a simple RNN layer including 500 layers, but we can use only 32 layers because here we have compressed data into tensors with 32 elements. So after embedding to compress the input tensors, we have just one recurrent neural network layer. And then dense layer, after compiling model, we train that and we can evaluate the model. As I mentioned here, we have just one RNN here, but it is possible to stack up several RNN layers in a model. As we can see here in the second attempt in this section, we want to build a model including 1, 2, 3, 4 simple RNN layers. So as you can see here, after embedding, we have tensors of with size 32. Then we create the first simple RNN layer, the second one, third, and last simple RNN. Here, in these intermediate layers, we set the option return sequences to true. In the lecture, I mentioned that we only consider the final output of the last layer as we use this final output as the final result of our model in RNN. But here, as we can see, each layer returns its own output. For instance, layer T-1 returns output T-1, or layer T returns output T. If we stack up RNNs like this, we should pass the intermediate output of all layers to the next RNN on top of this network. So here we have a network. For instance, this command creates a network like this. After that, we add one more simple RNN. This simple RNN, located here. on top of this RNN. So we set return sequences to true to, here, pass all outputs generated in these layers to the inputs of our new RNN network we have here. So here we give input value, and its output is given to the next RNN. So if you want to stack up several simple RNNs, it is mandatory to set the option return sequences to true. Why? Because we need these intermediate results for the next network. Okay, so as you can see here, we have one embedding and 4 simple RNN. For the first 3 simple RNN, the option, this return sequences options should be set to true because we need the output of every layer in the network, and after that we have one dense layer to obtain the probability distribution for reviews. Finally, in the last part of today's lab, we built a new model using LSTM RNNs. As you can see here, this script is exactly as the same as a script we have developed for simple RNN. The main difference is here. In simple RNN, we added a simple RNN layer here. But in LSTM implementation, here we have an LSTM layer. So if we replace simple RNN with LSTM, we have a model for review prediction using LSTM networks. Okay, we have one exercise. In this exercise, you are asked to play with, the structure of this network. So you can increase the number of layers in the model, or you can, anyway, you can play with the parameters of this model and see how, these changes impact the validation accuracy and the performance of your model. In addition, in the first part of today's lab, we have developed a network using dense neural networks. You can replace this using, maybe just think about that. How is it, if it is possible, you can build and train a model using CNNs, and then compare its performance against these models we have.